a whole new online school aimed at teaching sailors and boaters marine weather at a super high organized university-like level. And that's what the masterclass is about today. It's about sharing our knowledge and Chris's knowledge about marine weather with you, and giving you a taste of what we have in the university. We just kicked it off a few weeks ago. Basically, are rolling out a course every week all throughout the summer, and it will be essentially an online 24/7 school that sailors can take, and the doors are open. So without any further ado, let's get to the meat of the matter. Ladies and gentlemen, my good friend, Chris Bedford.
Wow, thanks, Peter. Thanks very much. Yeah, you and I have been around the block a few times together, and it's been quite an adventure. And this new program that Peter and I are working on, we're both really excited about, and something that I think both of us have been sort of mulling around in our head, and just right time came along, I guess. Not the best circumstances, but everybody's online and they're using this time productively. So let's try and do that today. Basically today, going to give you a little flavor for what we talk about in the Marine Weather University lectures, and sort of give you a little sample of some of the topics that we cover, and also try to sort of give you a little bit of sort of my philosophy and how we work with predicting the weather in today's world. There's a lot of information out there, and sorting through it becomes the main issue, and what it can tell you and what it can't tell you. And when it comes right down to it, it all gets backed up by the science, and having a foundation of understanding of meteorology is really important to getting the most that you can out of the weather forecast. So that's really kind of a summary of our goal here with Marine Weather University, is to let's go back to meteorology, get some of the basics so that we can add some value to the information that we get from the internet, for example. So with that, just give you a short overview of what we plan to cover today. I thought I'd start out by kind of talking about how most people prepare for their sailing, and you know, I work with a lot of sailors, from amateurs, cruisers, right up through some of the best sailors in the world, such as Peter. And so I see a wide range of approaches to this problem, but it turns out that most of it boils down to one thing. We're going to talk a little bit about that and what the limitation of that approach is, especially if you ignore the science. Then I'm going to talk a little bit about the art of interpretation, and that's where we sort of dovetail into the science, where the science comes into the picture. And as we go forward, I'll give you a little theory about how, or a little approach that most meteorologists use to making their daily forecasts, and the approach might surprise you a little bit. And then I'm going to talk about weather models, because they're such an integral part of our forecast process, but you need to understand some of the limitations of that. And I'm just going to give you a taste of that again in the university course, where we go into that in more depth. And then a little bit about preparation, being situationally aware, and what you want to do once you're underway. So let's get into that now, and let's talk about preparing for going out for a day of sailing, whether it be cruising or racing. And I suspect that these days, when you ask that question of most sailors, you say, well, how do you prepare to understand what the weather is going to be like when you're going to go out? Most of them will say, well, I check my weather app, or I check a couple of weather apps, whatever they have available to them. And that's great. Weather apps are wonderful tools. And so, I have a sample up here of what you might typically look at. So this happens to be sort of the SailFlow app. I use something called Wind Alert, which is another version of SailFlow. And, you start out, progressively with their app. And on the left side is a good way. It's a nice representation of the observations. This happens to be off of Galveston Bay in Texas. And, the reporting stations are shown there. It shows you the wind direction, the wind speed at each one of the stations. And then you can drill down a little bit and find out what's been happening at a particular station. If you click on it, and you get that screen that's second in from the left there. And that's the wind trace. So it tells you what's been happening over the last 3 hours. You can expand that to find out what's been happening over the last 12 or 24 hours. From there, you'll typically want to look at the forecast. So what are the models saying is going to happen at that particular location? So that's the third screen over from the left, and it gives you an hourly representation of what the model or a model is predicting for the wind speed and direction over time. Obviously, you're not going to be sailing at that one point. You're going to be moving around a little bit, so you might want to see how the wind is going to vary over that location. And this app is great. It gives you, like many do, gives you a representation of the model wind field and what that forecast looks like. And that's the last screen on the right there. So it gives you, and then you can kind of flip through it and see how that's going to change over time. Is it windier closer to the coast or offshore? How does the wind direction forecast to change? And this is where weather apps really shine. They give you good information on they give you information that's very well visually presented. And there are many different apps, and I find a lot of people find one that they like and that they can easily interpret, and that's the one that they generally use. There's a couple of things, though, you probably should be aware of when you're using any kind of weather app, and I call this a weather app quirk, but it's not really a quirk per se. It's just a reality of weather apps. You can have two different apps, but you will have the same forecast within them. I run across a lot of times people say, well, SailFlow is predicting this and Windfinder is predicting that. Well, you have to understand that a lot of times these apps are drawing from the exact same database. And so the forecasts are really going to be more or less the same. So here's a case that I show there. On the top is SailFlow app forecast, and on the bottom is a Windfinder app forecast, and pretty much they line up exactly between the two because they're both drawing from the same database. And if you're not aware of that, you should be, because it basically means that the app itself is really bringing data together into one place where you can access it. It's not necessarily unique data. A lot of these are drawing data from, say, the National Weather Service here in the US. And so they're going to be basically showing the same numbers, but in a different way each time. So there may be some small differences. Usually that's related to the fact that they may have to interpolate to the point that you've requested the forecast for, and there might be some small mathematical differences, but in essence, the forecast is the same. Another interesting little quirk, I guess, or maybe this is a feature of apps, is within the same app, you have different weather forecasts or different weather models. And different models will yield different results. And that's not really a bad thing, really. It gives you a measure of how reliable the forecast is. If you have two weather models that are different, then they are providing you two different forecasts. It can kind of tell you what the reliability or sort of the accuracy of the forecast might be. So if you have two models that are the same, the forecast is probably pretty reliable. If the two models diverge, then you basically have less certainty in the forecast, and your confidence is lower in the weather prediction, and that can be quite helpful. So here are two different weather models from the SailFlow, one app, two different models giving two very different forecasts. If you look at them over time, the one on top basically has a sort of a 9-10 knot wind most of the day, more or less from the southwest. The model on the bottom is showing a building breeze through the afternoon and the wind backing more from southwest to south-southwest. Again, helpful information because it says, well, there's something out there that could cause our steady southwest wind to change today. But without any interpretation or understanding where the data is coming from, you're kind of hard pressed to know which one is going to be correct. And so without that information, the usefulness of multiple models is a little bit limited. So you need to understand where the data is coming from. Then there's some other limitations that maybe you should think about a little bit more. And this really comes down to where we start to want to add value to the existing weather forecast. So let's look at the limitations of time resolution. So in a typical, what I have here is a wind trace over a period of 1 hour from 3 to 4 p.m. So on the left, you'll see a star for the wind direction that the app might predict. Let's assume the app was predicting the wind perfectly at 3 o'clock, and it said it was going to be from what's that, 315 degrees. And then at 4 o'clock, it also predicted it perfectly at 290 degrees. But look what happens to the wind between 3 o'clock and 4 o'clock. You can see that it's quite variable. The wind varies through a range of 275 degrees to 320 degrees. And sometimes those changes occur in less than 10 minutes. But the app, if you just had those two data points from the app, which is the most typical thing, is you'd think that the wind was going to back to the left by about 20-25 degrees over that hour. But as you can see, the wind is actually quite variable. And having been out sailing, we all know that the wind is quite a bit more variable than what you see in the app. The app makes it, if you have a data point every hour, it makes it look very simple. But the air is a lot more turbulent. So the best we can hope for the app is to give us a longer term trend. And this is often on a time scale that is more than the duration of a race. For example, if you have a race out there, you might only be racing for 30 to 60 minutes. And so the app doesn't give you all the detail that you might desire once you're out there. So there's a lot that goes on between the timestamps of the app. And then there's also the perception. So that's a limitation of the time. And so this is a matter of perspective. Let's assume you sail a 30-minute race within that 1 hour period. At 3:15, the wind direction is 290 degrees. And then you finish the race at 3:45 and the wind is 285 degrees. How do you perceive the character of the wind over that race? Now, the app would have said, well, during that hour, you're going to have a left shift of 25 degrees. But look what happens to the wind in that hour. It actually went left 5 degrees, but twice during the race, it oscillated to the right by 10 or 15 degrees. So how would you, if you were racing in that time period, how would you characterize the wind? You're probably going to remember the right shifts more than you're going to remember the left shifts in that race. And so the app basically hasn't given you much additional information. So it really comes down to getting out there and looking around you and understanding what's causing the shorter term shifts on the race course versus the longer term trend that the model might be predicting. And then there's the limitations of space. The model resolution is limited, and oftentimes we're sailing in a relatively small area. And so you may only get 1, maybe 2 grid points if you're lucky that are on the race course area. So here's an example of a race course in Biscayne Bay with a model overlaid, a typical model with 3-kilometer resolution. And so the best we can hope for here is some suggestion of how the wind might vary. You can see in this example, I've listed the actual wind speeds from the model of 7.7 along the inshore coast, and 6.2, 6.5 outside the bay. So a little bit lighter offshore relative to inshore. But that doesn't really tell you a lot of information. And as you know, from sailing in a small race course area like that the wind will vary quite a bit. And you'd like to know more than that. And again, it comes down to looking outside the boat and understanding what's going on versus just head down into a weather app. So this is where Marine Weather University comes in. What we're trying to do is kind of fill in those gaps. The models provide good, solid information, but unless you have a basis of the science, you can't add value to the weather app. So, Peter, I don't know if you want to break for any questions at this point and see what else we can add to this conversation.
Yeah, sure. Maybe we'll just throw one. Everybody's still getting into the room, but there were some questions about favorite weather apps, and I tried to answer it in text form. But basically, the message here is that apps are great. We all use them, but to understand the fundamental background of where the apps are getting information, what that information's limitations are, and realize that they are just one tool to use, and maybe not even the most important rule, and we all rely on them so heavily. And Chris, you work on the internet. I mean, you can call them apps. I mean, all of us use those tools, but it's the knowledge of how those tools work, just like a fine craftsman, that can give you the edge.
Yeah, for sure. We're all meteorologists because we have one of these. And as I tried to explain there. Huh?
Wait a minute. I thought a meteorologist had to have that coffee mug you had. Show that.
Yeah. You mean this one with the groundhog that says "not a meteorologist" on it? Yeah, the apps are great, and they help you visualize the weather data. But one app versus another app is not the answer, in my opinion. I think you really need to understand the science. And if you want to add value, you can take any app, take that forecast. But if you don't understand the science behind it, then you're really going to be pressed to add any value to the app. The app has limitations. The difference between a good forecast and a well-interpreted forecast are two very different things. So one of the things, and I think I come to this a little bit later in the discussion, is a weather app is precise, but not necessarily accurate. And that precision and accuracy are two different things. And what you want to do is, you may have an accurate forecast that isn't particularly precise, but that could be more useful to you once you're out sailing. So I'll just carry on and we'll have a little talk about this. The art of that interpretation is really where you add value to the weather forecast. So the technology is a tool. It's not the solution. So really, the arrow shouldn't start at technology and go to science. The arrow starts at science and goes toward technology. So you have to understand the science first and then be able to apply the technology to it. So you have the theory, that is the science. You observe what is going on in the atmosphere, observe what's going on around you. You model that, and you bring those pieces together in order to add value to a weather forecast. So having the best skill score is in a weather forecast is not necessarily adding value. Adding value is making the most useful forecast. And I think that means you have to leverage the observations and understand the science in order to make that leap. So as an example, one of the things that the thing that we start with in the Marine Weather University is talking about clouds. We don't start with weather maps. We don't start with understanding isobars. We don't start with models. We don't start with satellite. We start with clouds. That is, take all your instruments away except for these two right here, your eyes. Those are your best instruments you have once you're out on the water. And we talk about clouds. What are the different cloud types, and what do each one of those cloud types tell you? What can they tell you about the weather, whether it be in the next hour or the next 24 hours? You can actually make a reasonably good forecast if you understand what clouds you're looking for 12 or 24 hours in the future. It's not going to be accurate down to, 5 degrees and 1 knot like your weather app is going to show you, but you can actually make a pretty reasonable forecast without having looked at anything really other than the sky. So we talk about the different cloud types and kind of bring that down to the lowest level. And then once we've identified what the different cloud types are, we talk about what those clouds are indicating. And so here's an example again from the Weather University slide where we talk about cumulus, and they're one of the most common clouds you see out there, right? And what do they really tell you? Well, the cumulus themselves take on different forms. And so different cumulus will tell you different things about what's going on. Is it a small cumulus? Well, that means it's going to have smaller impacts on the wind. Well, what will those impacts be? Well, if it's a cumulus that's not raining, then it's sucking air into it. And we talk about a conceptual model where we have a cumulus cloud with an inflow into it to support an updraft that's supporting this cloud. And what does that do to the wind field surrounding it? And if you can conceptualize what that would do in an idealized environment, you can take that out into practice. And while it's more complicated and a bit more chaotic in reality, you can start to piece together the types of shifts and puffs and lulls that you might observe around a cumulus cloud. And if it's a raining cumulus cloud, like a rain shower, it's going to behave differently. And we talk about that in the Weather University. And then we talk about other types of clouds and the sequences that clouds appear in. So, for example, if there is a frontal system coming, you'll generally see cirrus clouds, those high wispy clouds approach first, and they may arrive 12, 24 hours prior to the front. And then as the front gets closer, the clouds start to lower and they get thicker and they turn into what we call altostratus clouds. And then eventually, as the front gets very close, we get nimbostratus. So we get clouds that are actually precipitating. So we talk about what the clouds are telling us outside of the weather app and what we can learn from that and how the winds will vary around that. And that's the real meat of bringing the science back into the picture and a basic understanding of science and observation before you apply a weather app. Any more questions at this point, Peter?
Sure, we can dive into it. The one watcher asks, it's hard to gauge what a small cloud is versus a large cloud without meeting one for the other. But I think that's your point. The point is to become, using your eyes to become more aware and armed with a little bit of knowledge, like that cool graphic of the vector addition of the cumulus cloud, and start being more sensitive and attuned to those messages, both that you're seeing in the wind on the water and in the clouds. You will become friendlier with those objects.
Yeah, for sure. Experience is a great teacher. So the more you're out in the environment, And the more you have an awareness of what you need to be looking for, the more you're going to make that connection. So a great example is, you know, a small cloud versus a large cloud. Well, what does that mean? Does that mean horizontally or does it mean vertically? And I can tell you right now, it's vertical that makes a bigger difference relative to the wind. It may be area-wise at the bottom, a small, relatively small cloud, but if it has great vertical extent, that means it has a strong updraft and has a bigger impact on the wind field. And that's the kind of thing that you learn through experience and being out in it. But the more you learn about how the clouds will impact the wind, even in a theoretical way, the more you can take that into practice once you're out sailing.
Talking about the high altitude, a couple people have asked about the high altitude winds and asking if how important it is to be aware of that when we sailors are concerned with winds at the surface. And another sort of side question similar was, what are your thoughts on using aviation weather forecasts to better understand how the wind is performing aloft?
Yep. All weather is three-dimensional. So what is happening upstairs does impact what's happening at the surface. So there is a need to understand what's happening aloft. How high you go probably depends on how long a forecast you're looking at. So if you're looking at you know, what's going to happen in the next hour or 2 hours, you don't need to look through a super deep layer of the atmosphere. If you're looking at what's going to happen in the next 2-3 days, then you need to look at a much deeper section of the atmosphere. And that kind of brings us into the next part of our discussion, which is something, it's basically a process that meteorologists go through to make a weather forecast called the forecast funnel. And the forecast funnel has basically two elements to it. One is scale, that is horizontal and vertical space scale, but also a time scale related to it. So when a meteorologist sits down to make the morning forecast, they don't pull up the latest weather model and say, okay, well, you know, the NAM is predicting this, the HRRR is predicting this. They don't do that. Basically, if that's what you're doing, you're not forecasting. What you're doing there is you're letting the model do the work, and you don't understand the science or why the model is making a prediction the way it is. So if something goes askew with the model, you're not going to have anything to fall back on to understand how to sort of recover from that. So a meteorologist sits down to make the forecast, and they start at a very large scale. They start pretty much, I guess, planetary, global scale initially, but probably more on a hemispheric scale. And then they understand what's happening at that scale, and then they start to narrow it down to the point where they're trying to forecast for the smaller area that they're trying to forecast for. So starting at a hemispheric scale, then going to what's called a synoptic scale. That might be the continental scale, for example. So if you pull up a weather map of North America, it's got the lows and highs and fronts on it. That's a synoptic chart. That's giving us the synoptic scale of what we're looking at. So we understand where the primary weather systems are that are driving the forecast. And then we start to go down to something called the mesoscale. And the mesoscale has a couple of subscales within it. But each one of those goes down basically, so you go from synoptic to maybe regional, say the Great Lakes, and then you'll go down to local, maybe Lake Michigan and the Chicago area. So you're basically narrowing the forecast down. And so this process here is kind of shown in this plot here. So if I was to start a forecast, I would, first look at the upper air charts, which give me a nice overview of where the primary weather systems are across the hemisphere. So in this case, it's covering North America all the way over to across the Western Pacific, and then across the Atlantic over to near Europe. And I can see where the primary weather systems are, where the big troughs and ridges, highs and lows are across that. And then I'll pull up the surface chart for North America, assuming I make a forecast in the United States. And then that shows me where the frontal systems are, the highs and lows. So for example, we can see that there's a frontal system sort of strung across the west from central Canada down through the Rocky Mountains and into California. And then another frontal system sort of sagging stationary across the southeast, and a big low just over eastern Canada. So this is a synoptic scale chart, and this allows us to sort of see where the main weather systems are. And then in addition to that, I'll start to look at what the satellite image is and what the radar is showing. So it's trying to add some detail, some sort of data depth to the forecast. And so that's sort of the start of the forecast funnel, and it'll continue on from there. So again, these would be the synoptic charts over a period of time. So I'm taking them and looking at them from the analysis on the left, and then how the meteorologists at the National Weather Service are expecting the systems to progress over time. And then I do similar thing with this weather site, which I really like, is called nowcastnoaa.gov. So here I'm looking at the satellite imagery across the United States, and I can zoom into a particular area that I'm interested in, has the radar overlaid, and you can get this idea of this funnel effect that I'm talking about, where I'm looking at the big picture first, I'm going down to the synoptic charts, investigating the forecast within the synoptic charts a little bit, and now trying to narrow down for the area that I'm actually predicting for. And in this case, again, this site, you can plot the observations so you can see how things are. Notice I have yet to touch a weather model. And it's important to me when I'm making a weather forecast, at least one that's maybe for no more than, say, 3 days. Once you get beyond 3 days, the weather models get a little bit more important in the forecast process, because it's hard to extrapolate beyond that. But I like to start my forecast before I look at the weather models. I like to have sort of a general forecast in my head before I actually get to the detail of the weather models. And again, I do that by basing it all on the science, the theory of meteorology. And once I have that, once I have a solid understanding of that, then I can add the models and start to look at the detail and what the models are predicting. So models are really great for helping to fill in the gaps. And there's a sort of an alphabet soup of many different models you can look at, which is great, but also can be quite confusing, because which one is right? that's the question I always get, is, well, there's this model, this one, which is the right one? And the answer is, we don't know. We don't know until the weather's happened which one is right. So this process that I go through, this sort of forecast funnel process that I go through, helps me to understand what the important driving factors are in the forecast, and that helps me interpret the models going forward. So let's talk a little bit how a model attempts to predict the weather. It does that by applying the basic physical, thermodynamic, and chemical laws. The atmosphere is basically treated as a fluid, and so it's all the laws and physics of that are quite well understood, and so we can apply those to the initial conditions of the atmosphere, and that can define the model for us. Probably the third bullet down here is probably the single most important aspect of weather modeling, and it's also the biggest source of error in weather modeling. And that is, in order to run a weather model, you have to tell the model what the current state of the atmosphere is. So you need to initialize the model with what's happening right now. Then you also, we'll talk a little bit more about why that's a source of error in a second. Then you also have to set up the terrain, mountains, hills, valleys, what type of surface, whether it be water or land, is it a plowed field versus a forest? And then something called geometry, which is basically a description of how you're going to solve the equations within the model itself. And obviously you need to have a very fast computer because you want your weather forecast to be done before you actually, to finish in the computer before you actually need it. Interesting story with the first America's Cup that I did with Peter is that to run a 12-hour weather forecast took 36 hours of computer time in a particular model that I was using. So not particularly useful. So the faster your computer, the quicker you can get that forecast out, and obviously the more useful it is. So once you have those things, you can basically turn on your virtual sun, turn the computer on, and it'll run these equations based upon the initial conditions that you've given it, and come up with a weather forecast. But there's a lot of limitations that get in the way of getting a perfectly accurate weather forecast. And as I said, the first one is that the initial state of the atmosphere can't be perfectly defined. We do not know what is happening in every sort of square centimeter of the atmosphere at any given time. We have a sparse network of observation stations, but we all know that the weather can change very dramatically from one location to another, even though they're relatively short distance apart. Another problem is that the atmosphere processes can't necessarily be explicitly modeled, so we have to make some assumptions in that process, and that can be a source of error, as can be just solving the equations. They're very complex, and solving those equations can create some errors. And then generally, nature is just chaotic. Sometimes it does things that we just don't know or understand about, which is also a source of error. So let's take a look at this problem with respect to the understanding the state of the atmosphere. On the left is a surface chart of the North Atlantic Ocean showing observations. And generally speaking, over most land areas, there's a reasonable number of observations, and that gives us a reasonably good idea of what's going on over the land. But when it comes to water, the observations are very sparse, and so somehow we need to fill in those gaps. And there's what's called an initialization process in a computer model that kind of tries to fill in the gaps. And one of the things that it uses is the prior model weather forecast. So if that was wrong, then it's going to carry on into the next forecast. And so somehow we have to fill in the gaps, and inevitably this is a source of error. So our biggest issue with weather forecasting is being able to tell the computer what is the initial state of the atmosphere. So that's a big problem. And if a weather model falls to pieces, then that's probably where it's going to do it. What do you think, Peter?
Yeah, it gives me bad dreams to look at the ship observations on top of a beautiful set of arrows from a model output, because it just, you invariably have these observations that are just at acute angles, 180 degrees and substantial velocity compared to the model. So it's good, better Better the devil you know than the devil you don't know, though.
Yeah, for sure.
There was a cool question about this, and the question was, could deep learning, artificial intelligence, have an application as weather prediction?
Um, I'm not necessarily a naysayer of that. However, I think it is, there's a lot of in the world right now of that's going to solve all our problems. I think it may raise as many problems as it solves. Um, Sort of AI is good with short range weather forecasts, say like 1, 2, 3 hours. Anything longer than that, it's sort of falls to pieces. The other thing about artificial intelligence is it has to have basically exactly what I just talked about. It has to have good representation of previous weather, and that's how it learns, right? But we don't know. There's certain places in the ocean where ships never go. So we don't exactly know what's happening there. And so if, that's a limitation. It's the same limitation that we're dealing with here. Now things are getting better. Satellites, we're getting more satellite data into the process. But even that is a problem because satellites sort of come and go, and their, funding is unsteady. So you might have a satellite that's working great for 5, 6 years, and then it stops working, but the next satellite isn't funded for another 4 years. So we're always dealing with this. An interesting thing that's going on right now, for example, is aircraft observations are used in weather models. So there's certain aircraft that are equipped with a system called ACARS, which takes temperature and humidity measurements, and then they also add in the wind from the movement calculation on the aircraft. And so every time a plane goes up and down, it produces this nice profile of the atmosphere. But there aren't as many flights now as there used to be pre-COVID. And so we're not getting that data into the weather models. And so weather models have suffered inaccuracy a little bit as a result. So there's a lot of problems, and a lot of them come down to this initial understanding the initial state of the atmosphere. If we knew what was happening in every spot, every time, we could make much better weather forecasts than we currently do. So what happens inevitably is you end up with different models predicting different solutions. So again, going back to that weather app example I gave earlier on, this is a plot from 2 different models of the wind across Long Island Sound for the same time. But you can see they're both predicting very different things. In certain areas, they match up quite close. Here on the Atlantic side of Long Island, the models, wind direction and wind speed, the blue barb is one model, the red barb is a different model. So down in this section of the forecast, they're predicting the same thing. And even up along portions of the Connecticut shore, they line up quite well. But if you look down here on the north side of Long Island, they're out by 120 or more degrees. So one basically is predicting a Long Island Sound sea breeze, and the other one is not. So which one is correct? Are they both wrong? And does it really matter? It's a valid question. Does it matter? You're getting good information from both these models, even though they're predicting 2 different things. They're telling you 2 different scenarios that could occur. And that's better than only having one model with one scenario, because if that goes wrong, then you don't necessarily have anything else to fall back on. So having multiple models is actually quite useful, but it can also be quite confusing, especially if you don't understand the meteorology that's driving the solutions of the models. And then here's a case where this is a forecast for a particular point where we have 50 models and 50 different answers. but we can put them all together and kind of summarize them and come up with statistics that show us areas in the forecast where the models are in good agreement, and therefore we have higher confidence in that part of the forecast. And then other areas of the forecast where the model is less reliable. So for example, where the spread between the models is very small here in the first 24, 36 hours, we have good confidence in the weather forecast. But then when we get, let's say, beyond 3 days in the forecast, you can see there is a bigger spread between the weather models. And so we have less confidence in the forecast. It may seem confusing, but it's actually good information to have. And again, this comes back to the precision of the models doesn't necessarily mean they're accurate, but if you put them all together, they're giving you valuable information that you can add to the base model forecast, and you can take out on the water with you with feeling better prepared, I guess. Peter, any questions?
Oh, that just brings back memories of sitting in your office every morning. The last cup campaign Chris and I did together, he would bring us in the morning and we'd have to sit through a version of the forecast funnel. It'd be like, no way we were going to go to this chart was the last thing we saw. And we started with the big picture. And I can't tell you how I love this presentation, the last Long Island Sound slide. The more you understand the science behind it, it just that last slide really tells the story. It told the story so well. I mean, there's going to be something happening in the middle of the sound. If you're racing, you don't want to bank on one weather forecast and say, here's what my routing says, go to the South Shore and all's good all the way out Long Island. You want to be able to explain when for sure the wind doesn't do what it's predicted. You're going to want to be thinking about looking at the sky, looking at the clouds, and coming up with an explanation as to why the initial plan went away and how you're going to adjust your plan. And with better science and better knowledge, whether you're looking at a multiple weather apps output like this or on the chart we just saw, you end up then, as Chris says, being able to add value on the team. Otherwise, it'd say, okay, just pitch him overboard. His app didn't work. Next.
Yeah, we don't want that. If I had taken that approach, I would have been pitched overboard 35 years ago.
There is another good question kind of related to this and that was, how do you judge your success, say, in a daily forecast? Do you regularly reflect, this is what I said and what happened and what did happen relative to velocity and direction? And do you grade yourself, or what's that process like? Must be hard being a meteorologist.
Yeah, you have to have a thick skin. You know, when I was younger doing this, I'd get very upset if I got a forecast wrong. Nowadays, I'm a bit more like, it's weather. But I don't necessarily judge myself on how I think the weather forecast was. And I go back to this adding value. So if the information, if at the end of the day, whoever I'm forecasting for feels that the information was useful to them, that's how I judge forecasts. If the information wasn't useful for them, then I feel like I haven't done a good job. And one of the is to make sure that I'm communicating uncertainty. And it's as important for me to admit what I don't know as it is for me to admit what I know. And that's good information. If I say you can bet the farm on it, I'm putting my reputation on the line. But if I'm honest with myself and honest about the weather forecast and the uncertainties with it, and it's actually, people can make smarter decisions, I think. They're not going to necessarily bang a corner. They're going to play a little bit more conservatively, not try to maybe cover more than trying to get the second or third shift down the course right. So I think that's how I judge myself. It's not so much in the absolutes and the skill score and that sort of thing. It's more about how, at the end of the day, did whoever I forecast for feel like that information was useful.
Good. Yeah, there was one other. Randy Needham asks, he was just aghast to find out that the forecasts on Long Island Sound aren't perfectly reliable. Dan Shear commented that asked it on a graph where you have a ton of models, like the next slide. Do you consider all the models equally likely? Do you ever weigh them differently? Do you have favorites?
Yeah, yes, when you this is called ensemble forecasting. So this is where you have a bunch of models and you apply them. When you walk into an ensemble forecasting situation, you walk in with the assumption that all models are equally probable before you start to just throw them out. Another important thing to remember is people that look at ensemble models will note, okay, well, this is ensemble E1. This is E2, E3. The important thing to understand is that particular run has no bearing on the next run. So models run off the 0Z data are independent of models run off the 12Z data. So sometimes people say, well, E1 has been doing well recently. Well, that's coincidence. And so you have to look at them each independently. And what I typically try to do is bin them into, okay, well, these models here, 30% of the models are generally predicting this, and 40% are generally predicting this, and then the other 30% are sort of outliers or all over the place. And I try to understand what those high probability scenarios are. That becomes my focus when I'm dealing with ensembles.
Cool.
So I can't leave a room without just talking a little bit about this, and this is the importance of preparation before you head out. This is pretty standard stuff here if you're in the United States anyway. Canada has similar service. The National Weather Service is an Environment Canada, for example, or whatever the national agency is where you are. They are the ones responsible for the official forecasts and warnings. So it's important that you check your official local forecasts before you go out. And most of the time, with a couple of exceptions, that's free information, and you should use it. There's weather websites in the United States. It's weather.gov. And then there's Environment Canada, the UK Met Office, etc. Make sure you're using that. And then if there's information available on your VHF, like there is in the United States, in Canada, the other countries have similar services. Make sure that you have that, what that frequency is, so that if you get out, you're sailing and things don't look right, you can always check in whether you're, whether or not you have internet access. You can check in on the VHF, what's going on. So the first thing that you have to do before you head out is become situationally aware and follow the checklist. So that means kind of doing this forecast funnel thing that I was talking about. Make sure you're looking outside. Does what's happening outside at the moment kind of fit within your understanding of the weather forecast? Make sure you're reviewing satellite and, if it's available, radar information, so you know where the primary cloud systems are, and note any nearby observations. So make sure you're understanding the situation that you're going out into before you actually go out into it. Then, as I said, once you've gone through that sort of funnel approach or that initial checklist, you can then review the models. But remember to place them into the context of the previous information that you just looked at. You know, does the model make sense based upon what's happening outside right at the moment? And then also keep the limitations of the models in mind. If you look at one model, that's called a deterministic forecast. That's one model, one forecast. But if you look at multiple models, then you have a probabilistic forecast. You have the probability of this scenario happening versus another scenario happening. And also always have some kind of a picture in your mind of how the weather is going to progress during the day based upon this review of the forecast, the local forecast and observations that you've done. Have that picture in your mind. And if things start to go different from that, your awareness should be heightened and you should start asking questions. So if the weather is not behaving the way that you had expected it, you should start asking questions and start finding out what's going on, especially if it's going in a bad direction. Then always make sure you have some sort of a backup plan or alternate in place. And then once you're underway, once you've left the dock, you know, forecasts become a little bit less useful because they're forecasts and they change. So keep your head out of the boat and go, as I said there, make sure that the weather outside is sort of following your general understanding of or general picture of how you thought the day was going to go. You know, I've never written a forecast I didn't want to immediately change. There's always new data coming in, and so the weather forecast is not a static piece of information. It's actually very dynamic. So it needs to be updated with the most recent weather information. And your observations outside of the boat of what's really happening around you are sort of the final piece of the weather puzzle. And that's, you know, those observations are really important. And perseverance is the courage to ignore the obvious wisdom of turning back. So make sure that you're looking out, and if things don't look right, you act accordingly. So monitoring the weather forecast once you're underway, again, you can do that on the weather radio. Compare your observations to the expectations of the forecast, and always leave an out. Just like your driver education teacher taught you, always have an out. Don't ever get yourself in a driving situation that you can't get out of. Same thing applies in sailing. Once you're out there, if the weather starts to go askew, make sure to be safe that you're you have another place to go. So just some safety information, really all about weather situational awareness that goes back to the weather forecast and your understanding of how the weather is should be playing out over the course of the day. With that, Peter, we can break to more questions or whatever.
Yeah, we're at the top of the hour, but they said we could go over a little bit, so let's do it. Here's a good one. Asking about the Marine Weather University. Will Marine Weather University teach and get into 500 millibar charts?
We will discuss them, yes, for sure. Again, that I think we're going to try and place that in the, it's very important to understand what's happening in the upper atmosphere because, as I said, what's happening up there has some impact on the bottom or on the surface where we're sailing. But you can put too much emphasis on it as well. So we're going to try and balance what you need to know with respect to upper level charts versus, you know, basically confusing you with too much information that you'll never use. So we're trying to make it as practical as possible.
Yeah, that guys is one of the things I'm most proud of what the curriculum that's coming together at Marine Weather University is how Chris is, for years this is his job. I mean, he knows a lot more about this than it takes 1 hour or 1 year to talk about. But he's thought long and hard and worked with a lot of sailors, thousands, probably hundreds of thousands of sailors over the years, and understands what our needs are. And the curriculum, it's so cool because it's really designed, it's the master chef style, it's Chris Bedford's spin on how you, the sailor who's not going to go to school and not going to get a master's degree in meteorology like Chris did, can raise your weather IQ. Another good question, seeing as though it's summertime, question from the Chesapeake Bay. We get a lot of late afternoon thunderstorms and local squalls approaching from the west. Can you describe how to predict what wind should and will do as a storm approaches and passes overhead? First of all, what's the best way to track it?
Well, radar is a good way to track thunderstorms. I'm going to say come to the Weather University because we talk about that very thing. Talk exactly about how wind behaves as a precipitating cumulus cloud, which is what a thunderstorm is, comes towards you. And the wind basically is outflowing from the thunderstorm cell. One of the mistakes a lot of people make, though, is to think of that as a static thing. This is this storm that's moving toward me. This is going to happen. But the reality is these storms oftentimes propagate. So this storm here will develop and start storming, and it'll create another storm. It'll be the impetus for the formation of another storm over here, and this storm here will die. And so these storms sort of breathe. They have a life of their own, and they come and go. And a lot of people make the mistake of thinking of them as static things that are just moving along and coming towards you. But and that can be a mistake because you might think you're in a safe spot, but this storm over here could generate another storm over here. So you have to be quite careful about that.
All right. Well, I think with that, we will begin to wrap up. I want to thank everybody that came out today. We really appreciate your interest and support. It's an important subject to us sailors, and Lord knows we can all learn more about the weather and benefit from it. And to the extent you're interested, please come and check us out. We have a section of the school at Marine Weather University where there's free classes and free resources, etc. In fact, I already posted it, but we'll plan on posting Chris's the deck of his presentation will be available in the free goodies section of Marine Weather University, so you didn't have to write down all those URLs, etc. And then huge thanks to our friends at North Sails. Both Chris and I have worked with them over the years a lot, and it's a great organization, great team of people, and they've done a lot during this strange period to help spread the word and help education. And this webinar series is one example of that. I do believe, and Louisa will confirm, that this session, the recording of this session, will be posted for posterity at North Sails YouTube channel. And so that will be great, and we really thank them for inviting us on board today. So with that, I did share a special coupon code for you seminar attendees in the chat room, 4th for North, only good through the 4th of July, but a discount for any class or course at Marine Weather University. So again, thank you very much on behalf of Chris Bedford and Marine Weather University. This is Peter Eisler saying so long for now from San Diego, and Louisa, back to you in Toronto, Canada.
You guys. Yes, this will be on our YouTube page shortly, and you can rewatch it for lots of good use and tips. And big thanks to Chris and Peter for sharing their knowledge today.